I'm Daniel, and this talk is going to be a little bit about static analysis, but it's going to be a short talk, so please don't fall asleep. I'm going to talk about unused parameters. Most of you should already know what unused parameters in Go already are. It's pretty simple. They're either parameters that you never needed, or you no longer need because you refactor some code, or sometimes a parameter is not being used when it should actually be used. For example, in this case, you should be writing to a writer, but you're actually hard-coding std out. Now, we could write a tool for this, right? Like a linter, like all of the other linters you can find online. So for our first version of this, I'm not going to be showing real code. I'm going to be showing pseudocode, because then it's easier to understand and easier to show. We're going to use the loader package, which basically only loads packages and gives you the files, the syntax trees. And we're going to use the AST package, the syntax tree package for Go, to analyze that code. Now enter our first tricky case. In this case, the body parameter is not used. If you can see, it's always overridden by another value. So it is kind of used in that second line in the body, but it is not the same value that it receives as a parameter. A human could really easily tell this parameter that is received is never used as it is. But to a machine, if you only use the syntax tree, it has no semantics. It doesn't know what each value is. It only knows names, and the name is the same, so it doesn't know that it's different. So our first algorithm would be something like this, which is kind of complicated. So we would iterate over all the functions, iterate over all the parameters, and then see if each of the parameters is actually used in any of the syntax tree nodes, in any of the expressions and statements within that function. Now, the limitations of this approach, as I mentioned, is first, we must do this manual search, this triple for loop that I just showed. And nodes read, this function that tells us what nodes are reading from names, whatever, variables. It is very complicated. It would actually probably be in the hundreds of lines of code, and it would probably not be very readable or precise or fun to maintain. So if we take our tricky case again, it's, as I mentioned, it's not a use of the parameter, it's a different value. And then we also have another problem with the syntax tree, and it's that there's so many ways to express the same thing. For example, if you declare a template struct, and then you assign a field to it, you can do it in a dozen ways, I'm sure you can imagine. These are just some examples. We can make this much simpler with the SSA package. I'm not going to go into what SSA is. If you're interested, just read the Wikipedia page. It's a very good introduction. But the basic idea is that all the variables are assigned exactly once. So the names always mean exactly one thing. And that simplifies a lot of things, especially static analysis. So in our case, because of SSA, the function would become something like this, which is that the assignment to body now becomes a new variable, body2. And now it's incredibly obvious, even to a machine, that the body you receive as a parameter is never used, because it's not used, the name is not anywhere else in the function. And the other thing that it does, which is really cool, is it keeps track of where you use each variable. So in this case, instead of doing a linear search, we just do a simple len check on the referrers, which means entities that refer to you. So if it's 0, nobody's using you. And there are some common sources of false positives. These are not particular to Go. These are common in all languages. One of them is dummy or stop functions. For example, suppose that you have a dev null type, such as the dev null on Unix machines. Whenever you write to that, you don't want to actually do anything. So the S parameter seems to be unused, but this is on purpose. Another common example is unimplemented functions. So you're still working on the code, or maybe it's unimplemented on purpose. So neither of these should be flagged by such a tool. And another one, which is pretty big, is when you have public APIs that you cannot change. For example, in Go 1, the standard library cannot be changed, because otherwise people's programs would stop building and running. But Go, as a language, has some fairly specific extra edge cases, and they're kind of similar to how Java has edge cases. For example, Java also has interfaces. But the difference is that Java's interfaces are explicit, and Go's interfaces are implicit. So whereas in Java, you could very easily see what you're implementing, in Go, you have to sort of find it out on your own. So the example that I wanted to show here is an HTTP server handler. And in this case, we don't care about the request. We always reply with the same thing. So we don't use the request parameter. But we still don't want this to be flagged, right? Because it's satisfying that interface, that function signature. And same thing with expand. Expand takes a function that maps from variable names to variable values, environment variable names. So in this case, if we always return the same thing, we don't want to flag this, because if we change the signature, if we remove the name parameter, it's going to stop compiling, because the os.expand expects exactly that function signature. Now, if we blacklist all known interfaces, either globally or the ones we can see from the imported packages, this is going to be way too conservative, because there are way too many function types and interfaces. We need to focus on the ones that may be used for a type, right? But what about type assertions and reflect? This gets very, very complicated very quickly. And once again, it's very complex code that you don't want to be writing. So enter our last package that I'm going to show you guys. It's called callgraph, and it builds on top of the one I just showed you, SSA. And what it does is it basically builds a graph of all the calls between functions. So for example, one function that is recursive would be one node that has an edge to itself. Kind of a silly example, but it can be useful. There are multiple algorithms you can use to build such a call graph. They have various advantages and disadvantages. For example, static, it does what the simple thing you can imagine in your head. Whenever there's a static call to something, it records that. RTA is a little more intelligent. It does the same thing, but incrementally, it also keeps track of other things like interfaces and reflect. But it builds from one entry point. So if your package is a library, it's not going to do anything useful, because a library can have any number of entry points you don't know beforehand. CHA, it's conservative, and it builds a conservative implements graph. So it says what could implement this interface instead of what is actually implementing this interface or being used as this interface. And PTA, the last one, it's the most accurate, but it's also the most expensive. And it's most expensive by a factor of, I think, 5 or 10x. So it is very slow. If you run it on something that had a regular amount of imports, for example, some packages from STD and a few extra packages from outside, it might take 10 seconds to do its thing. So it is very slow. And we want our linter to be reasonably fast and conservative. So for this example, we're going to use CHA, but it doesn't matter too much. Now, the last version of the program, I'm omitting the function loop here, so this is within a function. The only thing we're adding here is using the inbound calls to our function to see if any of the calls are strong. And strong is just a name, it's not a very good one, but basically what it means is this call meaning that I cannot change this function signature, that I cannot remove a parameter or anything like that. Some examples, for example, suppose that your function is being used as an interface, or sorry, as a function signature in this case, such as http.handler. If it's like that, if you change the signature, it's going to stop compiling. Another example is if it receives the parameters from calling another function, and then the same thing happens again. If you change the parameters, then the other function would also need to change its result parameters. So probably something would break along somewhere. And then as a quick summary, just to give the whole picture, is unused parameters, even though they might seem simple, and even though you might think the compiler should do it, they're actually very tricky. And I think it's actually impossible to get completely right, because there are lots of edge cases that you have to battle with. You should be using SSA to make your life easier. Callgraph also makes your life easier with the whole implements flow of things. And then the only thing you can do besides those things, unless you're a genius, is to rinse and repeat until the tool is good enough that you can reasonably say it's useful. That is exactly what I did for a little tool that I wrote about a year ago. It is still not very good, so maybe don't put it on CI because it's going to annoy you. But it is kind of part of the way there, so please do give it a look. And if you find bugs, do file them. Thank you.